Before a single volt flows through a new electrical substation, we must prove one non-negotiable fact. The physical panel wiring and the internal relay logic must be a flawless mirror of the approved engineering schematics. We are preparing to unleash a massive scale of energy into a new installation. The control logic governing that energy must behave exactly as intended, or the consequences of failure are catastrophic. To achieve this, we navigate a strict framework of reference standards from organizations like the IEC, IEEE, and NEMA. Often, these international standards overlap or conflict with specific project requirements. When they do, engineers apply a hard conflict resolution rule. You must apply the most stringent approved requirement. There is absolutely zero compromise on system integrity. But before any logical testing can legally begin, we must establish the primary safety prerequisite. Absolute physical safety must be secured. This requires the strict execution of lockout and tagout, or LOTO protocols. Equipment is locked out, safety warning boundaries are established, and proper grounding is physically verified before any panel is ever opened. Once safe, we begin the initial visual inspection phase. Engineers check every single connection point. They verify ferrule labels, test terminal tightness, inspect intact fuses, and validate the integrity of both the DC and AC power supplies. This clears the path for the general scheme check. The objective here is to sequentially simulate required inputs, one by one. This confirms that every local or remote command, open or close permissive, and system interlock triggers the correct fail-safe response. Establishing this rigorous physical baseline and systematically proving the logic is the only way to prevent unintended breaker operations once the substation goes live. With the baseline secure, we enter the active control testing phase. We start with the Automatic Bus Transfer System, or ABTS. The central rule governing this system is strict. It must enforce parallel limits, which typically restrict the grid to a maximum of 2 parallel transformers at any given time. This ABTS check table and diagram detail Case 1. 3 incomers are closed. The bus section switch is open. Simulating a fault changes the state to 0. If closed manually, ABTS automatically trips it after 30 seconds, maintaining parallel limits. Looking at Case 2 and 3 tables, we test how transfer logic adapts to different configurations. By altering initial bus section states, we verify specific responses to incomer faults, proving how manual reclose permissions are granted or dynamically blocked. This Case 4 diagram presents a critical edge case where all bus sections are initially closed, maximizing parallel capacity. Notice the highlighted switch S320. If 5 breakers remain closed for 30 seconds, the system recognizes a safety violation, automatically tripping. Verifying these precise time delays and blocking actions guarantees that the grid can safely manage complex power transfer events, preventing massive cascading overloads. Next, we test the Automatic Capacitor Control Scheme, or ACCS. This controller manages reactive power and maintains strict voltage thresholds by monitoring real-time bus conditions. This schematic outlines ACCS Case 1 with bus sections AB and BC open. A secondary injection test kit wired into controller inputs simulates live conditions. By injecting precise thresholds, we verify exact switching logic for isolated capacitor banks. Moving to Case 2, the system state is altered by closing bus section BC. This physical change forces the controller to adapt, evaluating an entirely different set of low-voltage capacitor banks to effectively manage the grid's reactive power. This logic table for Case 3 illustrates the specific MVAR settings used to verify the controller's response when bus section AB is closed and BC is open. During these validations, we also test the critical anti-hunting logic. We do this by deliberately fluctuating the injected voltage to see how the system reacts to erratic conditions. To pass this test, the ACCS must successfully block rapid, repetitive switching commands, ignoring the fluctuating inputs until conditions stabilize. Proving this anti-hunting logic ensures automated voltage stability for the grid, while simultaneously protecting the highly expensive capacitor banks from destructive physical wear and tear. We now transition to the passive protection domain. For high-voltage 380 kV infrastructure,
The engineering design requires strict point-to-point drawing validation. The tracing principle is absolute. We follow every physical wire from its source terminals directly into the primary protection relays. The physical reality must perfectly match the approved schematics. This 380 kV overhead line schematic maps the paths we trace from the current transformers on the left to the primary protection relays on the right. We verify line differential, distance, and breaker failure paths. Moving to the 380 kV busbar schematic, we trace the red lines connecting the vertical base circuits to validate bay CT selection and isolator status feeding into the protection zones. This diagram maps the 380 kV power transformer protection scheme. We trace the connection paths from the transformer cores to the relay units to prove the differential, restricted earth fault, and intertrip logic paths. Validating these primary 380 kV paths ensures that massive, high-voltage bus and line faults will be instantly detected and safely isolated by the correct relays. Shifting to the 132 kV infrastructure, this diagram for the overhead line and underground cable circuits highlights the dual protection strategy, showing the main 1 and main 2 protection paths feeding into the relay blocks. This schematic traces the 132 kV power transformer differential protection paths, mapping the complex wiring that terminates at the relays to ensure transformer stability. We repeat this rigorous tracing for the 132 kV busbar check zones, shunt reactor auxiliary alarms, and capacitor bank unbalanced protection circuits, driving toward the completion of tests 13, 14, and 15. During this tracing, the non-compliance rule is strictly enforced. Any missing ferrule, incorrect terminal reference, or drawing conflict is immediately logged as a punch item. It requires total correction and a complete retest.
Once the physical and logical checks are complete, we assemble the final evidence package. This compiles signed visual inspections, point-to-point trace sheets, alarm logs, and screenshots from the human-machine interface. We then reach the ultimate operational hold point. An operations witness must physically inspect the panel, confirming that it has returned to normal status. All test configurations have been removed, and there are 0 active alarms. A grid asset only achieves service release when every test result, log entry, and legal sign-off proves a flawless match to the engineering intent. Only then can the system safely interface with the live electrical grid.